Welcome to the deep dive. Today we're digging into an absolutely massive engineering story, one that spans decades and, well, literally goes deep underground in the Himalayas.
We are, yeah. We're talking about how facing an extraordinary challenge, building in the Lesser Himalayas, actually forced engineers to rethink everything based on just watching and learning over a long time.
It all centers around the Chhibro project. This was the first underground powerhouse complex in that region, started way back over 50 years ago. It sounds like it was a complete leap into the dark.
Oh, absolutely. Less of a standard project, more like a huge experiment. And the source material we're drawing on is a classic review of this pioneering work.
And central to this whole story is one key figure, Dr. Subhash Mitra. He was the chief engineer for R&D back then. His approach really set the stage for everything that followed.
That's right. Dr. Mitra had this fundamental philosophy, and it's worth quoting directly because it captures everything. Where theory, experience, and model studies fail to lead an engineer, observational approach provides them with a trustworthy torch. Powerful words.
A trustworthy torch. I like that. And that torch was fueled by what, 10 years of data? An incredible amount of information gathered at Chhibro from 73 to 83.
Exactly. 10 years. And our mission today is really to unpack what Dr. Mitra learned from that data, the concepts he developed for building underground in earthquake zones, basically how observation reshaped engineering in the Himalayas.
Okay, so let's paint the picture. Chhibro, what exactly was it?
It was a pretty substantial project, a 240-megawatt underground power station. And the location was key, deep inside this belt of dolomitic limestone. Not exactly easy stuff to work with.
Why underground, though? Was that just, preferable?
Not really preferable, more like necessary. Building it on the surface would have meant massive excavations on really steep slopes. Too risky, basically. Going underground was a safer, albeit more complex option.
And complex it was. The rock mass itself, it wasn't uniform, right? It was non-homogeneous, anisotropic, all those geological terms that spell trouble, plus tectonic stress.
Precisely. And remember the timing. Construction kicked off in 1966.
Way before the sophisticated computer modeling we have now.
Exactly. The source material is very clear on this. It says, and I'm quoting again, the construction of this powerhouse complex was considered as an experiment in prototype because there was hardly any rational method of design or any empirical or numerical method at the time of start of the project.
Wow, so they were figuring it out as they went along. An experiment in prototype. That really says it all.
And the geology just kept throwing curveballs. The cavern itself was in stratified limestone, which inherently has layers and weaknesses. Lots of shear zones.
Shear zones. Basically zones of broken, weaker rock.
Exactly. And there was a huge one, a major shear zone, 25 meters thick.
25 meters? That's massive.
It is. And it came incredibly close, within just 10 meters of the lowest part of the structure, the draft tube level. That's a serious vulnerability right there.
And wasn't there also a concern about a huge chunk of rock falling from the roof?
Yeah, the initial analysis predicted a potential 16-meter-high triangular rock wedge detaching from the crown. Imagine that. So you've got weak zones nearby, potential roof collapse.
It sounds like a nightmare scenario. The existing methods, the empirical rules like Terzagh's, they just weren't up to this.
No, not for the Himalayas. Terzagh's methods are great for certain conditions, more stable rock masses. But here, with the complex geology, the anisotropy, the tectonic activity, they fell short.
And this is where Dr. Mitra steps in again.
This is his crucial insight. He realized, that guesswork based on unsuitable models wasn't going to cut it. The only reliable path forward was observation. Long-term, detailed observation.
So he planned and implemented this major instrumentation program.
He did. He knew they needed real data from the site itself over time to understand how the rock was actually behaving. Yeah. That was the game changer.
Okay, so 10 years of monitoring in the Himalayas. That must have been a huge undertaking. What kind of instruments are we talking about?
It was quite sophisticated for the time. They used a network of imported instruments. The source calls it the MDS system. This included things like strain meters to measure deformation, rock bolt load cells to see how much force the bolts were actually taking, extensometers, measuring movement across joints or cracks, and pore water cells to track water pressure changes within the rock.
And they kept this up for a full decade, 73 to 83.
Continuously. Which, as you said, is a feat in itself. The source actually makes a point that often huge amounts of field data get collected on big projects.
But nobody actually sits down and properly analyzes it.
Exactly. It says voluminous field data at several projects is seldom analyzed carefully by the researchers. But Dr. Mitra was different. He didn't just collect the data, he dove into it. His analysis is what unlocked its great value.
And what was one of the first big takeaways from all that data?
One of the immediate big findings was about the support systems, how different types performed over the long haul. He really clarified the distinction between passive and active supports.
Okay, passive versus active. What did the data show?
It showed that passive systems, think rigid things like the steel ribs and the concrete arch they used in the roof of the cavern, they actually attract more load over time.
They attract it. How does that work?
Well, they're passive, right. They only start resisting significantly after the rock moves and pushes against them. So over time, as the rock creeps or adjusts, more and more load gets transferred onto these rigid elements.
But they use them in the roof, which seems like the most critical part. Was that just the standard approach back then?
It was pretty standard, yeah.
Yeah.
Especially for providing that immediate stability right after blasting and excavation. But Dr. Mitra's data really highlighted the long-term downside.
Okay, so what about the alternative, the active systems?
Active systems like the pre-tension cable anchors and rock bolts they used in the walls, often combined with shotcrete, performed much better in the long run. The data showed they were likely to encounter lesser long-term support pressures.
Right, because with active systems, you're tensioning them before the rock fully relaxes. You're essentially knitting the rock mass together, making it support itself, rather than just putting up a passive barrier.
That's a great way to put it, stitching the rock mass together. It becomes part of the structure, rather than just load acting on the structure.
Yeah.
A really fundamental difference revealed by the long-term data.
That difference alone seems huge for design philosophy.
It was, and it led directly into Dr. Mitra's next major insight, which was about how support pressure changes over time. Time-dependent pressure.
Ah, yes. You mentioned engineers used to assume a constant ratio for long-term pressure increase, something like 1.7 times the initial pressure.
That was a common rule of thumb, yeah. 1.7.
And Dr. Mitra's decade of Chhibro data.
It blew that assumption out of the water completely. His analysis showed that ratio wasn't constant at all. It varied hugely.
Hugely? Like, how much?
From 1.7, yes, but all the way up to 5.9.
5.9, that's almost 6 times the initial pressure. That's an enormous difference for design.
Colossal. It meant structures potentially needed to be much, much stronger than previously thought to handle the long-term loads. And he figured out why it varied so much.
What were the factors?
It depended heavily on seepage conditions, how much water was flowing through the rock. Also, the nature of the fillings in the rock joints, especially if they were soluble and could wash out or weaken over time. And, crucially, the type of support system being used, tying back to that passive versus active finding.
So water was a major player in this long-term pressure increase.
Absolutely critical, especially in the roof section with the passive supports. The data showed this significant time-dependent effect was primarily driven by water saturation in the rock mass.
And where was the water coming from?
Two main things showed up clearly in the stress data. First, the obvious one, monsoon rains. Every year, the monsoon would recharge the groundwater system in the rock, increasing seepage and pressure.
Okay, that makes sense. Seasonal effects. What was the second factor?
This one was tied to the power station's operation, the amount of water being drawn for power generation. During peak generation periods, drawing more water actually created extra seepage pressure in the surrounding rock.
Wow. So the operation of the powerhouse itself was actively changing the stress conditions in the rock around it over time.
Precisely. It wasn't just static load, it was dynamic hydromechanical interaction. Dr. Mitra proved that when the rock mass gets saturated, its modulus of deformation, basically its stiffness goes down, it gets weaker, effectively.
And that's something designers absolutely have to account for.
They have to. And it was something that the standard empirical methods back then, like Barton's Q system, didn't fully capture in these saturated, complex conditions. They often focus more on the quality of the intact, dry rock. Dr. Mitra's work filled a critical gap by highlighting this long-term water effect.
Okay, so we have passive versus active support, the huge variability in long-term pressure, the critical role of water saturation. This already feels like a revolution in understanding. But then came the earthquakes.
Right. The Himalayas are obviously seismically active. And Dr. Mitra observed something puzzling. Even after the initial stabilization, the pressure on the supports near that big 25-meter shear zone kept creeping up over time.
Even without a major earthquake happening.
Exactly. And he developed a really novel explanation for this. He attributed it to the cumulative effect of all the small recurring earthquakes, the ones that are magnitude 5 that happen pretty frequently in the region.
So not just the big damaging quakes, but the constant background shaking was adding up, like micro damage accumulating over time.
That was his hypothesis. Each small shock might only cause a tiny adjustment or strain accumulation, especially near a major weakness like that shear zone, but over years and decades, it adds up to a significant increase in pressure on the supports.
That's a fascinating idea. It's one thing to hypothesize, but did he manage to quantify it?
He did. This is where his most, perhaps, groundbreaking theoretical work comes in.
Hmm.
He didn't just observe. He developed a new empirical theory, an actual equation, equation 1 in his paper, to predict this additional seismic support pressure. He called it delta peak.
An equation to predict pressure buildup from small cumulative quakes near shear zones. That sounds incredibly specific and useful.
It was. And it wasn't just a simple formula. It forced engineers to consider factors that hadn't really been systematically included in this way before.
Like what? What went into this delta peak calculation?
It incorporated the joint roughness number due in your wall, basically how rough or smooth the rock discontinuities are, which affects how they slip or lock up during shaking.
Okay, makes sense. Rougher joints might resist better or worse.
It's complex, but roughness plays a definite role in shear behavior. The equation also included the overall rock mass quality, QAll, a measure of the rock's general stability. And the really crucial part, the total number of small earthquake shocks expected over the structure's entire lifespan, say 100 years.
So he was building long-term cumulative seismic risk right into the design calculation for support pressure. That feels revolutionary.
It absolutely was. It was quantifying the effect of persistent, low-level seismicity on long-term stability, especially near geological weak spots.
And then, as if on cue, nature decided to put his theory to the test.
Yeah, I could say that. In 1991, the Uttarkashi earthquake hit, magnitude 6.3. Not right at Chhibro, but about 100 kilometers away. Close enough to give the structure a significant shake. The source perfectly calls it a God-made seismic test.
The ultimate validation opportunity. What happened at Chhibro? Did the theory hold up?
Amazingly well. The powerhouse survived without major structural failure, but there was minor damage and measurable deformation. And crucially, it was concentrated exactly where Dr. Mitra's theory predicted the highest vulnerability.
Right near that big shear zone.
Exactly.
Yeah.
They observed minor cracking and recorded significant rock deformations. The extensometer showed movements of 1 to 4 millimeters, primarily in the areas closest to that underlying 25-meter thick shear zone.
Just as his cumulative pressure theory suggested, the weak point showed itself under seismic load.
Precisely. The accumulated strain made that area more susceptible, and the numbers matched up too.
How so?
The estimated increase in support pressure near the shear zone, calculated using Dr. Mitra's delta peak equation, was between 21% and 23% of the existing long-term pressure. And the observed pressure increases after the Uttarkashi quake. They're right in that ballpark.
Wow. That's incredible validation, from theory based on small quake accumulation to prediction confirmed by a real moderate earthquake.
It really cemented the value of his approach and his specific theory for seismic design in these challenging environments.
So, summing up Dr. Subhash Mitra's legacy here, it feels immense. His work at Chhibro, analyzing all that data so meticulously, really did bridge the gap, didn't it, between abstract theory and the incredibly complex reality of building inside the Himalayas?
It absolutely did. He established principles for designing support systems that weren't just about holding up rock right after blasting, but about handling long-term creep, the effects of water saturation, and crucially, the dynamic cumulative impact of earthquakes over decades.
The key takeaway for you listening seems clear then. Engineering theory is vital, but as Dr. Mitra demonstrated, its real value, especially in complex places like the Himalayas, is unlocked only through rigorous long-term field observation and verification.
Exactly. His observational approach, his willingness to let the mountain itself teach him through data, provides lessons that are just as critical today for anyone planning, designing, or building major underground works in seismically active regions.
Okay, so we've seen how Dr. Mitra proved active supports like cable anchors are generally better long-term, especially against creep and water effects compared to passive supports. And he gave us equations to account for cumulative seismic pressure near weak zones. So here's something to think about. How essential are Dr. Mitra's seismic pressure equations, delta P, today in ensuring that our modern, sophisticated active support systems are not just stable, but truly resilient enough to withstand a century's worth of earthquakes in the Himalayas?